That is, early on in my quest to find out which area of science I wanted to pursue as a career. I'm sorry, I got rid of something. Just a moment. Well, I was saying, these scientists are the reason I'm here today giving this talk. And early on in my quest to find out which area of science I wanted to pursue as a career, when I first was introduced to these scientists' laws and theories of gravity motion, I fell in love with the physics. And that basically sealed my faith in my becoming an astrophysicist, one that studies the physics of the universe. Let's get started. So my agenda will be, first I would talk about how I was motivated to study this area. And then I would give you general background on black holes, actually the historical background of how I got involved in it. And then I will give an overview of what black holes are and the formation of black holes. And I would talk about non-rotating black holes and rotating black holes. Then I would talk about the energy extraction mechanism, and I will conclude and finally take questions. So my motivation was quasars. Now, quasars were discovered in 1963, and I'll talk more about their properties later on. But quasars appear to, well, we categorize them into two categories. We observe radio strong quasars, which are associated with jets, and then radio quiet, which are not associated with jets, and they are radio quiet in the electromagnetic spectrum. And we believe, since we're looking back in time, we believe that these radio strong evolved into radio galaxies, and then the radio quiet into super galaxies. And all the whole class, including quasars, are AGNs. So the general background, okay, black holes. Historically, there has been two ways to extract energy from the black hole. From the accretion disk, and that includes binding energy, the release of gravitational binding energy, and orbital differential viscous forces, and magnetic stresses. And then the second way is the Penrose mechanism. Now, Penrose, in 1969, he proposed a way to extract energy from a rotating black hole. So he didn't work it out, and I'll talk more about the Penrose mechanism later. And so when I first got into this and studying the literature, I found a lot of work on the accretion disk models. However, there was very little work on rotational energy being extracted from the black hole. And the reason why is because this would require general relativity. So I just, from reading the different literature and stuff, and I kind of just formed this, from looking at the different literature, I formed this, I guess, like, I asked the question, so what about black holes? And I just assumed that relativists were asking the same question. So we were saying, like, you have a 10 to the 8 solar mass, supermassive black hole, and yet it appears that it has no significant role in producing the spectra of AGN, or active galactic nuclei. So I took on the task of finding out the effects that the black hole could have on the spectral observations of AGN. And this work began when I was in graduate school. So after looking at all the different models and actually trying to work out some of the models, I ran into some of the same problems that they were having. So the two popular models were the Penrose mechanism and the Blanford-Znajek type model. So I started working on the Blanford-Znajek type model, and I ran into a problem that I could not create the particles that were needed in order to explain the spectra of AGN. So my only other way would be to work on the Penrose mechanism. I'm sorry, I should have cut this off. So from studying the different models, I came up with this goal. So this was going to be my dissertation. So the first part of my dissertation, I was going to create a model to explain the core energy source of quasars and other active galactic nuclei. And the core is the center. And so that this part of the goal would be to extract the particles, since the Blanford-Znajek model cannot create particles under the theory of accretion disk, because it needed a magnetic field that was comparable to that of a neutron star. So that was the first goal. I had to create a model to extract the particles out. And then the second part was I was going to create a consistent model to explain the generation of the polar jets that we observed to be emerging from the cores of AGN. Okay, so here I will give an overview of what black holes are. Okay, black holes were predicted to exist from Albert Einstein's general theory of relativity in 1915. In a nutshell, general relativity, it describes motion in a gravitational field. It shows that clocks run slower in a gravitational field, and it shows that space-time is curved around an object. And so I'm sure some of you all, many of you all probably saw the rubber sheet analogy. So here, this is the way Einstein looked at gravity. So here you have this rubber sheet, and you have a mass here. And so if you have a rubber sheet, you put a large mass in the center, say a steel ball or something like that, then it's going to sink. And Einstein theory says that these are orbits, these are trapped orbits, and the mass is there. Isaac Newton's laws, or laws of gravity, says that gravity is a force at a distance. So that's the difference between the two. Okay. Okay. I'm not sure why my, okay. So black holes are one of the most fascinating objects in our universe. They are a storehouse of a tremendous amount of energy. It was not until the 1990s that we began to understand the physics of black holes. My work of 1991 and subsequently contributed significantly to our understanding of black hole physics. For example, it showed how energy is extracted from the black hole. So it produced an energy extraction mechanism. It's used in the general relativistic magnetohydrodynamic simulations. That's what that means. That's the acronym. It could describe it provided the equations to describe the merging of compact objects, like for example, two black holes merging that we observed to show that gravitational waves exist. And it provided the simulations for the near event horizon simulations inside the ergosphere. And when I first started working on black holes, they had not been confirmed to exist. And so in 1994, observations by the Hubble telescope confirmed that supermassive black holes indeed exist in nature, and that they are at the center of most galaxies. Black holes, their masses can range from greater than 3 times our sun's mass in a galaxy to the size of a galaxy. and they are at the center of galaxies, and they range from from greater than 3 suns masses. That's for a galactic black hole, and the up to 1,000,000 times our sun's mass. So in addition to gravitational stored energy, black holes can have rotational energy and electromagnetic energy. And we have something that we call the no-hair theorem, which states that the only thing that we can ever know about a black hole is its mass, its angular momentum, and its charge. So for example, say a supermassive black hole, we don't know if it formed from, say, a supermassive star, or did it form from a cluster of stars that eventually evolved into black holes and then merged together. So black holes are believed to power the most energetic objects in our universe, such as quasars and gamma ray bursts. Now, again, quasars were discovered in 1963, and they are the most distant objects in our universe, and they have a very large energy output. The energy output, say the luminosity, is about 1,000 times that of our galaxy, yet they are no bigger than our solar system. So that means that they were for a long time mysterious objects. They are associated with polar jets of very high energy particles, such as electrons and photons, and perhaps protons. And we observe or detect a magnetic field. So magnetic fields are important. And the reason why we know magnetic fields is there because of the synchrotron radiation. And also these objects have a lot of non-thermal radiation. And so we believe that Compton scattering processes are taking place. So here I'm just going to go through a gallery of the objects that I'm going to talk about. So this is a quasar. This is another quasar, and let's go back to this one. Okay, so you see the jets emanating from the core, and a lot of they're one-sided. Some of them are one-sided, but they are actually two-sided. But one is Doppler boosted. The energy is Doppler boosted when the jet is pointed towards our line of sight, and this one is redshifted, so that's why we don't see the jet part. Okay, this is another diagram, and the black hole would be there, and these are the jets, the polar jets. Okay, this is another one. So here you see the jet, and then you can barely see the counter jet. And this is an artist's conception of a, this is like a Seyfert galaxy. So like the radio galaxy. Okay, and this is taken with the Hubble telescope, and this is a core showing the core of a galaxy and the black hole there. Okay, and this is just to show you that galaxy with the black hole, and this galaxy looks similar to our galaxy, and our galaxy has a black hole also. Okay, this is an elliptical galaxy, and most of the galaxies with jets are the elliptical galaxies. So now I want to say something about gamma ray bursts. So gamma ray bursts were discovered in the 1970s, and they appear to be the most energetic events in the universe. And now we believe that that gamma ray bursts, it's different kinds of gamma ray bursts, the short and the long, but all of them are associated with black holes or the birth of a black hole. So the supernova explosions prior to the formation of a black hole. You can have two neutron stars that collide to form a black hole, and or you can have a neutron star being swallowed by a black hole. So the gamma ray bursts, again, they're also associated with black holes. So I'm just going to go through this quickly because this is probably something that you all already know. Okay, so black holes are formed by dying stars. Once the star has depleted its available hydrogen at its core, in which it was converting hydrogen into helium by nuclear fusion, once the available hydrogen is gone, then the star starts to collapse under gravity. And if the star is about the size of our sun, it will collapse until electron degeneracy, and that is the electrons are all in the lower quantum state, and they put up a pressure to halt the collapse. And what we end up with is a white dwarf. And so a white dwarf is, because it's made of a high pressure crystalline carbon, they're actually diamonds in the sky the size of our Earth. And again, a teapot, not again, but a teaspoon would weigh about 2 tons. Okay, so the way that a star dies, I'm sorry, the way that a black hole forms depends on the mass of the star. So if the mass is greater than 3 times our sun's mass, then a neutron star will form. And then the electrons are not able to halt the collapse, but the neutrons in the nucleus are able to halt the collapse with nucleon degeneracy. And that's the Pauli exclusion principle at work. And so neutron stars, they end up with very large rotations and very large magnetic fields. And when the pole is pointed in our direction, then they're called pulsars. And so a black hole will form if the mass is about 10 times greater than our sun's mass. And in this case, once the nuclear fusion has been depleted, or the hydrogen has been depleted, then it starts to collapse. And so in this case, the neutrons are not able to halt the collapse, and gravity and the star continues to collapse, and gravity takes over. And eventually the gravity increases more and more as the star collapses until the gravitational field is so strong that light cannot escape. And then in this case, we have a black hole forming. So this is just a diagram of how the light rays are not emitted towards us, but are trapped by the black hole. Okay. So non-rotating black holes. Right after Einstein published his theory, Carl Schwarzschild, he worked out the physics for a black hole, a non-rotating black hole. And so here, if you were coming in from, say, far away from the black hole, in this case, you would encounter a photon orbit, and this is where light is trapped in a circle by the black hole. And usually light travels in a straight line, so it just shows you the large gravitational field present. And then you encounter the event horizon. Now, the event horizon is the so-called surface of the black hole, but it's the surface where anything that falls in cannot escape. In order to escape from the black hole, it would have to have a velocity greater than the speed of light. And then here you have the singularity. And this is of infinite gravity and infinite density. And we call it singularity because there our physics break down. So we don't really know what happens to the core until we have a theory for quantum gravity, and we don't have one right now. So rotating black holes. So we extract energy from rotating black holes. The physics of rotating black holes was worked out by, from Einstein's theory by Roy Kerr. And sometimes we refer to the rotating black hole as the Kerr black hole. And so here, coming in from very large distances, when you get close to the black hole, you encounter a region called the stationary limit. And if you go within the stationary limit, anything that falls into this stationary limit must rotate in the direction that the black hole is rotating. So you cannot define a place of rest in this region. And so anything that falls in, we see it going around the black hole. And as it gets closer and closer to the event horizon, it spins, it rotates or orbits faster and faster. This region is called the ergosphere. And the reason we call that ergosphere means energy sphere. So from this region, you have, or in this region, you have particle orbits. And these particle orbits can actually extract energy from the black hole. And this is where I do my work inside the ergosphere. And then here you have a ring singularity, and of course the event horizon. But still, anything that falls within the event horizon cannot escape, even though the singularity is here. And then there's some other stuff about it being repulsive, and you go in and you'll go to another universe and stuff. Well, I don't really work with that, but general relativity does tell us strange things like that. So the important properties of rotating curved black holes. So a lot of this I've already said. So for an infalling particle as measured by a distant observer, the distant observer would see the infalling particle being dragged around, okay, faster and faster about the event horizon. So before reaching the horizon, you encounter the ergosphere. Now, even though energy is always measured even though energy is always positive, for a infalling particle inside the ergosphere, the particle can have negative energy. However, this negative energy never leaves the ergosphere. But a particle with positive energy can leave the ergosphere. And that's where the Penrose mechanism comes in. Now, so I talked about, I said about the, actually the stellar-sized black holes. And what we observe these stellar-sized black holes, and they actually look like, we call them microquasars because they have jets like quasars. And so they were discovered in 1991. I'm gonna put my glasses so I can see. They were discovered in 1991. So this is just given the masses. So for supermassive black holes, you have masses from 10 to the 6, a million times to a billion times. And then for the microquasars, the masses are from 7 to 20 times our sun's mass. Of course, the luminosities are different. Now, black holes are scale independent. So if you do express things in units of mass, you have the same physics that you have in the quasars as you have in the microquasars. The variabilities are shorter for microquasars as opposed to the quasars. And so by studying the microquasars, since the variabilities are shorter, and these can expand and decay, the jets in these objects can expand and decay for periods of less than a month. So from studying the microquasars, it tells us something about the quasars. The energy ranges are different, and that's for the quasars, it ranges from radio to hard X-rays, and to hard gamma rays. And that's because of the processes going on in the accretion disk, and I'll talk something about the accretion disk. So this is a microquasar, and microquasars usually are associated with the binary system, and so this would be the accretion disk, and matter is being drawn from, a binary star companion. And the energies are not as high, and that's because of the accretion disk. Less matter is being accreted, but the physics are the same for the quasar and the microquasar. Okay, this is just a diagram where I'm showing you, and of course it's not drawn to scale, but this is the accretion disk. Now matter is accreted onto the black hole and it falls into the ergosphere. And this is the thin accretion disk, and it's cooler than this region up here. This is the iron corona. This happens because of the instabilities that are taking place that heats up the thin disk, and it radiates like our sun's corona here. And this is the way particles are escaping from the core. I'm not gonna go through all of that. So this is an artist's conception of a black hole system or quasar system. So here, this is actually observation, and this is the artist's rendition of the of what we would be observing. And this is based on theory. So this is the accretion disk. Okay. In one model I'll talk about, these would be magnetic field lines, but in the Penrose process, these would actually be particle orbits. And this is the artist's conception of space-time being dragged around. So when you come into reaching, and when you come inside the ergosphere, then space-time is actually dragged around. And that's what causes the particles to rotate faster and faster, or orbit faster and faster. And it's because of frame drag. Now, this is another picture of an artist's conception. So here, these actually could be either particle orbits or magnetic field. And the way that we measured this is because it's from rotation measure. So the rotation measure consists of the electrons number density, the number of electrons per unit volume, and the magnetic field, because they are like multiples, it's like we don't, it could be either magnetic fields or particles. And so our theories and further observations will tell us which of the two is more important. And then also it suggests that it could be a combination of both of magnetic fields and particle orbits. Now, this is a picture of this is actually an observation of an image of a black hole. And I'm sure you all have seen this taken by the Event Horizon Telescope. So this is the black hole shadow here. And this region, this is a reflection of the particles from the photon orbit. And so actually it's like the photon orbits, like from gravitational lensing. That's why we can actually see the whole surface, but part of it is coming from the back of the black hole shadow. And this radiation here, this is synchrotron radiation coming from the photon orbit. So that's important that you all keep that in mind. And then this is the polarization image. And so again, these particles, like here, this could actually be magnetic field lines or particle motion. So since nothing can escape from the event horizon, the identification of a black hole is its gravitational influence on nearby matter. So historically, there are two popular models and two popular competing theoretical models proposed to extract energy from a rotating black hole. And that's the Penrose mechanism and the Blanford-Znajek type mechanism. So first I would talk about the Penrose mechanism, then I would talk about the Blanford-Znajek model, and then I would talk about my contribution, and I call that the Penrose-Williams mechanism. And I explained to you why I called it that. So in the case of the classical Penrose process, you have a particle that's inside the ergosphere. It breaks into two particles. One particle is trapped, the other particle escapes. The particle that's trapped has a negative energy. So from conservation of energy, E1 is equal to E2 plus E3. We have this relation. So if we solve for E3, the particle energy that escapes, then you have E3 is equal to E1 minus E2. But if E2 is less than 0, then E3 is equal to E1 is equal to E1 plus the absolute value of E2, because E2 is negative. And so you see that rotational energy, we see that rotational energy is extracted because E3 has an energy E1 plus the energy of E2. So in that case, rotational energy is extracted. However, there were problems with the classical Penrose process. Number one is that we found that the breakup would have to be relativistic, near the speed of light. So a star just couldn't break up and undergo the Penrose process. So in order to overcome that, then we said, okay, so we'll do relativistic particle scattering. But then we found out that, well, actually we'll let the particle, we use relativistic particles to break up, and then they will break up at the speed of light. But we found out the efficiency was very low in this process. So to overcome these problems, I investigated relativistic scattering, in which I looked at or investigated inverse Compton scattering and Penrose pair production, in which electron-positron pairs are produced. Okay, so now we'll talk about the Blanford-Znajek type model. In 1976, Blanford-Znajek proposed a model to extract electromagnetic energy from the black hole, and then subsequently the Blanford-Payne model to extract electromagnetic energy. So here, the Blanford-Payne model says that if the magnetic field, now all of this is the magnetic field from the accretion disk, because the black hole does not have a magnetic field, because the magnetic field is trapped inside the event horizon, and the field that was outside decayed quickly. So you only have the magnetic field of the accretion disk. So here, if Blanford-Payne says that if this angle is less than 60 degrees, then particles can be flung out by a centrifugal force, like beads on a string. And then, since it's a theory, or actually experiment, that says that we call it the Meissner effect, and I'll talk about that after this. But the magnetic field lines, they were not anchored to this part of the black hole, but they could anchor to the polar region. But you would have to have an accretion disk to ram pressure the magnetic field inward, or have particles take it inward. And then by some unidentified or a lot of hand waving, you actually have the magnetic field being twisted around. And the theory goes that, or the hypothesis says that as these field lines tighten, then the particles are attached to the magnetic field and they are pushed up along the polar axis out to very large distances. So that's the Blanford-Znajek type model. The main problem with the Blanford-Znajek model or process is that it extracts electromagnetic energy, not particle energy, and not electromagnetic radiation, but electromagnetic energy by way of a punching flux. And let me just go back. So the punching flux is, you can get a power or luminosity in this electric field crossed with the B field. Okay, so again, you have punching flux and not particle energies needed to agree with observation, because what we have observed is that electron-positron pairs are emerging from the cores of these objects. And it's a mystery as to where these electron-positron pairs are coming from. I'll stop there and then I'll go on to explain it. So the main problem with the Blanford-Znajek model is that it doesn't extract particle energies, but electromagnetic energy. So, and more problems with the Blanford-Znajek type model is that it lacks the high energy particles to form the jets in the phonal region that are void of dynamical accretion disk particles because of centrifugal, okay, I'm sorry. Centrifugal, okay, variant, which says that the particles, as they are being accreted, it forms a phonal region. And okay, this would be the funnel region would be like this. And because of the centrifugal force, it keeps particles from this region. And this is the region where you would need particles for the Blanford-Znajek model to work. So also, it lacks a large strength, large scale disk magnetic field, because we don't observe a large strength or large scale magnetic field. So you would have to have that in order for the Blanford-Znajek model to be efficient. Okay, and also that the model have to have the magnetic field brought in from the accretion disk, and then you have theoretical physicists saying that the accretion disk only brings a low value magnetic field to the black hole. So this is what they call the Meissner effect. And it's like the Meissner effect in electromagnetism, where as a system is, as the temperature increases, it becomes a superconductor, and it expels the magnetic field. And so this is just showing where if you have a uniform magnetic field, you put a black hole there. If the spin is small, it will intercept the black hole. But as you increase the spin, then the black hole repels it. And so here is the electric field, and then as you increase the spin, the electric field that's induced also is expelled by the black hole. So that's a problem with the Blanford-Znajek type model. So at the present, such models are extremely complex and cannot be self-consistently described or qualified to compare with observations. In other words, there are too many loose ends to qualify it as a complete theory to extract energy from a black hole. And importantly, the Event Horizon Telescope observations measures a magnetic field strength of about 1 to 50 Gauss, which is very much smaller than that required for the Blanford-Znajek process to occur. And the magnetic field would have to be greater than or equal to 10,000 Gauss to produce the needed electrons for synchrotron radiation. So if the field is large, say comparable to a neutron star, then it would be easy to produce those particles, but we do not have that around the black hole. So the Penrose, now this is my model. The Penrose-Williams mechanism, it was proposed in 1991 in my dissertation, and then I published the results in 1995. And then in 2004, I published that the particles are escaping in these vortical jets. Now, remember, my goal was to create a consistent model to explain the generation of the jets. So at first I was going to use like a Blanford-Znajek type model once I got the particles out. But after I got the particles out and I was looking at studying how my particles were escaping, then I found out that they were actually escaping in orbits, in vortical orbits. The jets were actually produced by the black hole, and that's due to gravity. Okay, so this model is a four-dimensional general relativistic model, mathematical model, which uses space-time frame dragging, and it appears to overcome problems associated with the Blanford-Znajek type model. This model is self-consistent, and it constitutes a complete theory to extract energy from the black hole. So now let me just explain it. Okay, so here, this is the funnel region that I was talking about. And particles are actually void from coming into this region from the accretion disk. So here's the ergosphere, and then this is the thin accretion disk, and this is the ion corona. So particles fall in here, and they escape from orbits inside here, and because of the frame dragging, they escape in these vortical orbits that are encircling the polar axis. And the particles are actually following these orbits. The particles are actually on these types of orbits from the frame dragging. And that's the ergosphere. I'll explain that a little bit further. Okay, so this model, it consists of a curved black hole, a supermassive black hole, 10 to the 8 times our sun's mass, plus particles from the accretion disk. And we're assuming that the accretion disk is a thin disk iron corona. The difference in the difference in the thin disk and the iron corona is that the iron corona have very large temperatures, and the protons in there can have temperatures up to 10 to the 12 Kelvin, and the electron, the temperatures go up to first they're 10 to the 12th, and then the electrons have a more effective cooling process, so they are cooled down to about 10 to the 9th or a billion Kelvin. So the Penrose mechanism is used to extract energy by scattering processes inside the ergosphere. So here, this is a black hole, and this is the diagram just to show you the radii where the scattering processes take place. So this is the static limit. So anything falling there rotates in the direction that the black hole is rotating. And this is the marginally stable orbit of the accretion disk. So this is the last stable orbit. And the orbits in here are unstable. Then you have the, okay, in here you have the marginally bound orbit, and this is the last orbit for any particle, material particle. Then you have the photon orbit, the last orbit for any particle, masses or material. So in this region is where I do Compton scattering processes. And here I just kind of show, but I got a better diagram. But in Compton scattering or inverse Compton scattering, you have the electron, the photon comes in, scatters, the electron is put on a negative energy orbit or a lower energy orbit, and the photon escapes with energy outside, escapes to outside the event horizon to infinity, which is us. We're called the observer at infinity. And so in this region is where we do Compton scattering, and then the pairs, I do electron-positron pair production. This was pair production in the field of in the Coulomb field of the nucleus or the proton. This process was not feasible, so I won't mention that one anymore. But the one that was very feasible was the Penrose pair production at the photon orbit. And in this case, you have a gamma ray that's in a bound orbit at the photon orbit. And I call that that's the target particle. Then you have an incident gamma ray coming from the accretion disk, and they pair produce into electron-positron pairs. So the astrophysical importance of this model is that it can predict spectral ranges of particles intrinsic to black hole radiation by the Penrose mechanism. Okay, so the overall results is that I was able to obtain the force momentum, which is the energy of a particle, particles, and I did a up to 2,000 scattering events, and you'll see that the reason why I stopped at that number is because I wanted to be able to see the results as opposed to the particles just filling up the area, and I'll show you what I'm talking about. So I was able to get the energy, the 3 space components, momenta of the particle. And so that's the radial, the theta component, okay, which measures from the polar axis, 0 to 180 degrees below the black hole. And then the azimuthal component. And so with this, I'm able to get the energy and the structure of the jets from these momenta components. And so Penrose Compton scattering for these small energies, 5 eV to 1 MeV, million electron volts, I was able to obtain energies from 15 keV to 14 MeV. and for Penrose pair production, in which the here again the target particle and the incident particle, and from this process, I was able to obtain energies up to 54 GeV for the iron corona when using the iron corona. My computer, my mouse is very sensitive. And then for energies of 3.5 kV up to 50 kV, I was able to get energies up to 54 GeV out from the gamma pair production. And now remember, this is done at the photon orbit. So this is basically a prediction because no one had ever done this before. And I was only able to do it because of the equations that I had solved for the trajectories at the photon orbit. And then I found out while studying studying what my particles would do, and in the process of creating a time evolution, I found out about the vortical polar jets, and I found out from a conference that I had gone to in Israel, and this person, Fernando Di Felice, after I gave a talk on this subject, he came up to me and directed me to a paper that he had published. And the paper was describing these vortical jets that should be escaping from black holes. And then that's what made me realize and understand that that's what my particles were doing, that they were actually escaping in these vortical orbits. So I confirmed his theory, and his confirmed mine. Okay, so now these items 1, 2, and 3 are all consistent with observations. Okay, so it's found that these Penrose scattering processes exhibit escaping vortical orbits of relativistic particles, concentric and collimated about the polar axis. So this would be the these are vortical orbits, and they're escaping from, this is the marginally stable orbit, and then these are gamma rays are escaping from out here. And then the photon orbit, this is where I do the pair production, and they are escaping. So the marginally bound orbit and the marginally stable orbits contains gamma rays, and this central part will contains electron-positron pairs, and this is where the synchrotron radiation is coming from. So, and what we observe is actually, they call it a spine. So we actually observe two mechanisms that are creating these regions, and one's creating the spine and another process is creating the sheet. So my calculations are consistent with those observations. Let's see what else. Okay, so these angles that you see, these very small angles, you will see that they are, when you look at it, you know, without considering the vortical orbits, it appears that the particles are escaping at these small angles, but they're escaping outward, say in the, you know, if it's towards the equatorial plane, it would be in the equatorial plane. But then when you look at it like these are actually vortical orbits, then we know that these are like coils. Okay, these orbits are like coils. So the radial component would define the narrowness of these. The theta component would be the coil-like, because that's in the polar direction. The azimuthal component would be the tightness of the orbits. And then also what we found, and I'll show you, that these particles are escaping in these vortical orbits with velocities near the speed of light. So that gives us the relativistic particles that we observe to be escaping. Okay, now, there's always been a problem of lifting the particles up into the jets. Now, what I found from the Penrose mechanism is that the gravitomagnetic field, now this field was proposed before my work, but the gravitomagnetic field is a gravitational analog of a magnetic field. And so when the object is not rotating, you have the regular gravitational acceleration to the center, and that's G. But when it's rotating, you have an additional force, and this force is associated with space-time rotation. And so, or what am I trying to say? Well, I'll just go on. It's associated with space-time rotation. And so, oh, okay, a rotating frame. That's what I want to say. So when you're in a rotating frame, there are what we call fictitious forces. So it's the centrifugal force, and then you have something called the Coriolis force. So, so in a rotating frame, and because the frames are dragged around, you have these additional forces. And that force, the Coriolis force, is the force that the gravitomagnetic field, it's the gravitational or general relativistic version of that Coriolis force. And I found that this force has repulsive, this force has is repulsive in the polar direction and in the radial direction. And so this force, it actually it acts on the particle's momentum. Now, what's different from the an electromagnetic field is that the magnetic field acts on only charged particles. The gravitomagnetic field, it acts on all particles, independent of their charge, because it acts on just the momentum of the particle. So also, the reason why we call it a gravitomagnetic force is because, I'm sorry. I should use the pointer, but else it'll be the same. Okay, and so the far away from, this is how this force would look far away from the horizon. And so here you have the this is the gravitomagnetic field acting on a particle moving with velocity. Now, this field only acts on particles that are moving. And so here you have the gravitomagnetic force, and then you have the Lorentz force acting on a charged particle, so you can see the similarities. So just as the gravitational force causes local inertia frames to fall with acceleration g, the gravitomagnetic vector field causes local inertia rotating frames to rotate with this angular velocity here. And this H is a force field that drags local inertia frames into rotation, and as a result produces a Coriolis-like force. So that's the reason why we call it a gravitomagnetic force. It has nothing to do with gravity. I mean, I'm sorry, electromagnetism, but because the forces are similar, we call it that. And also the lines, these are the lines of the gravitomagnetic force. So it look like a magnetic force. Okay. This equation, you don't have to know all of it. And I want to mention that the only reason why I'm talking about the gravitomagnetic force field or have it separate from the calculations is that I just wanted to show the effects of it. But I don't have, in my calculations, I don't have to separate it because the curve metric takes care of all of this and produces the properties that I'm talking about. So this is in the this is the gravitomagnetic force in the radial direction. And notice that if you look, this is in the radial direction. That term is 0. So you can see that this vector, it acts on the azimuthal component. Now, that's the component, that's the largest component, and that's the component that causes the orbits to be vortical. And so the larger the polar coordinate of the momenta, the greater this force is going to be. That's in the radial direction. Now, this is the force in the polar direction, which is important in the generation of the jets. So here you see, so this is down here. Well, actually, these are angles down here. So this is a function of the polar coordinate angle. And so you have a force in the in the polar direction, in one direction, okay? So if the black hole is rotating and the pole is here, this would be the force in that direction. And then this is the force in the opposite direction that would produce the counterjet. And the larger the polar coordinate, which is what we extract the rotational part, the polar coordinate contains the azimuthal component contains the rotation that we are extracting. And so the larger that rotation, the greater that force is going to be in the polar direction. So that's how you get particles in the polar direction and subsequently in the jets. So once the particles are escaping in these vortical orbits, now Newton's first law, actually the angular momentum is conserved. And so if these particles are not acted on by some force or torque or some outside force, they will continue from that initial acceleration that it obtained from the black hole and the gravito-magnetic force. So I most likely, since I haven't done a time scale evolution, most likely these forces, now this is the artist's conception, but these would be the vortical orbits. And then eventually when you get outside the frame dragging, the angular momentum is probably transformed to linear momentum. And the magnetic field, okay, so when they're escaping in these vortical orbits, the magnetic field would be in the polar direction. Okay, we're just using electrodynamics now. So the magnetic field would be in the polar direction as the particles are escaping in these vortical orbits. And then eventually, once they're outside the frame dragging effect, then these particles, their angular momentum is probably transformed to linear momentum, and then the magnetic field would be in this direction, will be circling the pole. And so that's what we actually observe. Once you get outside the far away from the black hole, it appears that the magnetic field is like a helix, becomes like a helix. So it goes from in the polar direction and the particles are in the helical orbits. Once outside the frame dragging, then the magnetic field probably takes the place of the helical orbits and the particles are in the Z direction or the polar direction. Okay, so these are results from my these are the results from my my calculations. So here, this is just the, I know that this is probably hard to see, but these will be this is the luminosity as a function of the energy or the frequency. And so these are from observations. And so here, this is this part would be the accretion disk. These are quasars 2C379 and 2C373. So this would be the accretion disk. Then we have another region where radiation is emitted, electromagnetic radiation. This region, and then you have another region where electromagnetic radiation is emitted. So this is in the X-ray and this is in the gamma ray. And so here again, this would be, these are observations. So it seems to be like in the high energy, it's three regions, okay? So the Penrose process, Penrose-Compton scattering would cover this region, and the Penrose pair production would cover this region. Now, those from observation. So these are from my model over here. So this is the accretion disk. These numbers are the continuum where my particles are emitting radiation. So this is the Penrose-Compton scattering by equatorial targets. This is Penrose-Compton scattering by non-equatorially confined particle targets, where the particles, they're not confined to the ergosphere, but they actually orbit outside the ergosphere. They pass, I'm sorry, the event horizon, not ergosphere. So these particles are here. Okay. So these particles are from inverse Compton scattering. And that a scattering of target particles that are confined to the equatorial plane. These are particles, these are scattered from particles that are not confined to the equatorial plane, or electrons not confined to the equatorial plane. And then these are due to Penrose pair production, where the energy from the electron positron pairs, I was able to contain a luminosity as a function of the frequency. So these lines right here, this is if I had every particle escape. Every particle scatters. So once I take into consideration that not every particle is going to scatter, then I'm able to fit these results to observations. And so you see the three reasons of observations where we observe spectra. The Penrose process actually creates particles in those three separate regions. And so that's 3C279 and 3C273. So it's similar. So in other words, I'm able to get luminosities that are consistent with the what we observe. And luminosities are powers, the energy per unit time. Now that was for a supermassive black hole. This is from a galactic black hole or a micro quasar. These are observations. That's the accretion disk. That's the alpha K iron alpha K line. I think I'm saying that right. Okay. So this is okay. So that's the accretion disk. Then you have particles that are, you have some mechanism that's creating these particles. Okay, this is the energy is increasing. Then you have another something that's creating these particles that are separate from this. Okay. And so here, this is my my model. This is from my model, and this is the spectrum that I create from my model. So this is the accretion disk. So if you take a particle or monochromatic energy from this region or this part of the spectrum and undergo the Penrose-Compton scattering with say 2,000 photons, okay, or scattering dense, you get this distribution. And this distribution is similar to this one. This is just showing instability, how the from instability, the spectra or the luminosity increases. And so this is Penrose-Compton scattering here. And then this here, this would be this curve, and that's due to Penrose pair production. You don't see that third curve in there. I mean, that curve that I had in the middle of the other ones, okay. Like here, and that's due to the iron corona. And so what my calculations tell us that the microquasar, the accretion disk, does not undergo that, does not have, or the energies or the temperatures do not increase to that of a corona. So here you don't have those electron positron, the electron, you don't have Compton scattering from the non-equatorial targets, because those targets would be part of the corona. And for the galactic black hole or microquasar, it appears that the corona does not normally exist. Now, these are the plots, or like scattering plots of the momenta. So each one of these dots is a particle, escaping particle from the scattering event. So you see why I didn't do any more scattering, because it just would have filled in the circle, and I wanted to see what the particles are actually doing. And those are the consistent, the corresponding energies. So these are the radial components, and this is what we get. And you can see, like, this line is the equatorial plane, not necessarily equatorial plane. This line distinguishes the radial components in the that's directed inward, are the ones with the negative radial components, and then the ones with the and the ones above this line are the positive ones. So a large number of the particles are scattered and escaping toward the equatorial, toward the event horizon. However, they're not falling into the event horizon because they're on escaping orbits. And so they are actually directed toward the jet or the polar axis. Okay, this is of the polar coordinates. And here you can see when the energies are low, you have just this distribution. So this is the polar coordinate in this direction. As the energies increase, then you have the polar momentum increases and the angles would actually be increasing. And I'll show you. So that's the polar coordinate. This is the azimuthal component, and you see the azimuthal component is linear to the energy. So the higher the energy, the larger the azimuthal component, and then the larger that gravitomagnetic field would be on the particles. Okay, these are the polar angles. And so you see, when I was saying it looked like, now this is the 90 degrees, so this is the equatorial plane. So it looks like the particles are actually being emitted toward or escaping toward the equatorial plane. But if you consider, that's in 2 dimensions, but if you consider that the particles are escaping in 3 dimensions, then these would be like the helical angles of escape. And these angles, right, as you increase the electron's energy for the non-equatorial targets, then the maximum angle is that of the electron in their, they call them spherical-like orbits, where it goes to a certain momentum. The polar coordinate goes to 0, and then it circles back down, passes through the event horizon, goes to a latitude below the equatorial plane, and then the process just continues. The orbits that are trapped. Okay, these are the radial components for the Penrose pair production. And so each one of these is an electron, and that's in the radial direction. And they can only escape outward because they're at the scattering is done at the photon orbit. And so anything that falls in is just going to fall into the event horizon. Is anything that's directed that has a negative radial component is going to fall in. And these are the polar coordinates for the electron-positron pairs. And you see as the energy increases, the polar coordinates increase. This is for the azimuthal component. It's a function of the energy. I mean, it's linear to the energy. And these are the escaping angles for the electron-positron pair. Now, these escaping angles are like the maximum angle is 0.5 degrees. So these particles, they have very small angles, and that means that the coil is close or tight. So that's like the sturdiness of the jet. And they are also moving near the speed of light. Okay. Where am I? The time. Okay. Okay, so this is the velocity distribution of the escaping electron-positron pairs, and this is after 2,000 scattering events at the photon orbit. So these are just the parameters, but here you see this is the velocity measured in units of the speed of light, and these are their gammas, and you can see these are little dots, but they are all together. But these are individual escaping particles, and so you see they asymptotically goes to the speed of light. So they're relativistic particles. So what are the results from the Penrose-Williams mechanism? Okay, the escaping high energy electrons are expected to create a self-induced magnetic field producing synchrotron radiation in the form of vertical swirling jets consistent with the Event Horizon Telescope observations. The escaping electrons can act as seed or loading particles, allowing the Blanford-Znajek type model to operate. And at best, it will enhance the Penrose mechanism in further collimation and accelerating the particle plasma out to the observed distances of the jets. Okay, the Penrose mechanism does not need Blanford-Znajek type model to extract energy from the black hole close to the event horizon, where indeed gravity dominates. A frame dragging can produce symmetrical or possibly asymmetrical uneven jets about the equatorial plane. And I could show you that with that equation that I had for the gravitomagnetic field. But in the case of a curved black hole, that the parameter that would allow that to happen is 0. So the curved black hole couldn't produce the Earth, the asymmetrical jets. At least the curved metric couldn't. But if the metric is derived, say, and does not assume reflection symmetry, then you could probably get asymmetrical jets from this model. So there are no problems exist thus far with the Penrose-Williams mechanism, and it is consistent with Event Horizon Telescope observations. Okay, now this I'm finishing the talk. So so importantly and in summary, okay, my theoretical analysis of the Penrose mechanism of 1991, my dissertation 1995, laid the groundwork for the advancements we have made over the last 2 decades in understanding general relativistic astrophysical rotating black holes. My contributions consisted of 1, creating a theoretical, analytical, mathematical general relativistic model that successfully extracts energy momentum from the ergosphere of rotating black holes by the Penrose inverse Compton scattering and the Penrose electron-positron pair production at the photon orbit. Okay, so that to extract energy from the photon orbit, the Event Horizon telescope is now observing that. So it's basically confirming that part of my my model. Okay, also it contributed to creating a 4-dimensional Monte Carlo computer simulation of the model to show that high energy particles escape in the form of bipolar jets consistent with observations of quasars and other AGN. So in other words, after I did my theoretical analysis, then I created a Monte Carlo computer simulation. Monte Carlo means like sampling, where I sampled different angles, because once the scattering takes place, the particle can be be scattered in any direction. So I was able to, from the computer, I did the Monte Carlo where I sampled. So it was like random, doing a random derivation, or look at I guess like randomly selecting the angle, because the particle can be scattered in any angle from 0 to 180 degrees for the polar angle until and then from 0 to 2 pi for the azimuthal angle. So that's what the Monte Carlo did. It chose those angles, and then I was able to get the energy. So I created a 4-dimensional computer simulation of my model, and then from that I was able to show like what the particles are actually doing and how they're escaping. And I was able to do it not just for one particle, but for as many particles as I chose. And okay, so it also my contribution consists of deriving analytic expressions for the conserved energy and the conserved angular momentum for non-equatorially confined circular trajectories or orbits about the rotating black hole. So before my calculations, we could only do calculations that were confined to the equatorial plane. So once I solved for the conserved energy and angular momentum, I was able to look at the particles as they escape from the equatorial plane, or escape above and below the equatorial plane. Most important, these derived conserved energies and angular momentum were the first to solve the equations of motion that were that Bardeen et al. Gave in 1972 for matter being accreted onto a black hole in 4 dimensions using general relativity, which provided the blueprint for the gravitomagnetic hydrodynamic type simulations that we, I mean, some of you are probably aware of but they have been making great progress using my derived equations or parameters. So such simulations, the gravitomagnetic hydrodynamic and the gravitomagnetic radiative transfer, in etc., simulations are now being used to confirm general relativity with the event horizon observations and to predict properties that should be observed. And so again, these are the observations. That's the first one. M87, which is an active galactic nuclei. And it's one where the jet is pointed almost toward us, the line of sight of the observer. And then these are the polar coordinates, the polarized radiation. And here, this is consistent with my model of the vortical orbits if we're looking down the jet. Okay, so conclusion. Okay, we now have evidence that black holes exist in nature. Black holes that exist in nature are most likely rotating. Supermassive black holes are indeed fascinating objects in the universe and might be the heart of galaxy formation. Because the black hole, our observations suggest that the black hole and the galaxies are somehow related. One more. Okay, so it appears that energy momentum is extracted by Williams' analysis of the Penrose mechanism and perhaps enhanced by the Blanford-Znajek type mechanism. And I'll end there. Thank you.
Yeah, thank you. That was very interesting. And there's probably people who have to leave. So I'm going to excuse them, but if there are questions, we have one already. Okay, so if you have to leave, go ahead. But yeah, so we have one question coming up, at least two. Yeah.
Okay.
You're welcome to come up. Yeah, sure.
So how valid are these solutions for a charged black hole in the Kerr-Newman metric for general relativity?
Right. Okay. Before I found out that my particles were escaping on these vortical orbits, my next project, I was going to use the Kerr-Newman black hole and repeat the same calculations that I did for the Kerr black hole. But I ran into problems because the physics was, I ran into some physics that I couldn't solve. Okay, I couldn't separate. It was very messy. Okay, and then as I applied for grants, the feedback I got was that the Kerr-Newman black hole is going to eventually charge out. Okay, unless it has a magnetosphere, and that's kind of like speculation. But I didn't get very far with the Kerr-Newman black hole trying to do this process. But now, that was like years ago. But now, possibly if you could find out a way to have a magnetosphere, okay, that would keep the particles, that would keep the charge there, you could probably, these processes, they may work, but then you have to also consider like that the particles, like the positive charge particles, are going to be accelerated in one direction and then the negative in the other direction. So it can become very messy, but I would not discourage anybody from working on it because, it may work. Thank you for your question.
I have another one too.
Okay.
Is there any like limiting rotational velocity for the process to work, like too fast or too slow? Because I think as you get to a faster rotational speed, you'll start getting rid of parts of the ergosphere, if I remember correctly. So is there a limiting rotational velocity for that?
Okay. Like your question. Okay, let me just try to rephrase it. Okay, like with the Blanford-Znajek type model, or a particle model that actually actually extracts just rotational energy, then through electromagnetic processes, then eventually the black hole would slow down. okay? But when you have an accretion disk, in the case of this model, you have an accretion disk. As long as you have accretion disk, it's a canonical spin where it's 0. I don't know if you're familiar with the angular momentum parameter, but anyway, it's 0.998. That's the value. And so once the Thorne did a theoretical calculation that once the rotational energy is extracted, okay, then the particles from the accretion disk will come in and speed the rotation back up. Okay, if the rotation is if it gets greater than that, then the particles from the accretion disk will slow it back down to this canonical value. So as long as you have like an accretion disk, then the Penrose mechanism would work. Okay. But once the accretion disk is depleted, then the black hole actually turns off. Okay, now you did mention magneto rotational instability. Did you say something about that?
I was curious if there's like a limiting case when you get to a high enough velocity, rotational velocity, that you get some extra, if it like does anything weird with the frame dragging that already isn't being done with the frame dragging, to the point where you like warp you basically like get rid of the event horizon or anything like that if you're getting close to like a naked singularity, or no?
Yeah, well, the naked singularity, like this curved black hole, it doesn't have a naked singularity. Mm-hmm. So I didn't study that part. Okay, I did study about naked singularities. That was early on, but they don't, I reached the conclusion from studying the literature that they really don't exist in nature. Okay. So there's a lot of things that general relativity states, like negative singularities, but then like they're not realistic as far as nature goes. Okay.
Cool.
Does that kind of answer your question?
Yes, it does. Thank you very much.
Okay, thank you for the question.
Anybody else? Okay, I'm gonna let everybody go. I'm gonna ask you one question when they go. So if you don't mind, if you've got a moment. Yeah. All right, thank you again. Actually, my question is, it's kind of refreshing to see a advanced astrophysical thing that doesn't mysteriously rely on magnetic fields. So many things you just explain away by saying, oh, there's lots of twisted magnetic fields or something. Kind of refreshing to see that that's not the issue. It's kind of replaced with a frame dragging issue that provides the vorticity, I guess, instead of the magnetic fields. Yeah, so that's kind of nice. Did you have any interaction with the LIGO people with the colliding black holes stuff?
Well, I mean, I did. I didn't work on LIGO, but Kip Thorne and we have a history. I don't know, y'all probably heard about it, but I didn't work on the project.
I see. Okay.
LIGO. But I'm sure. Well, I've seen papers and stuff that they were actually, using my equations for the non-equatorially confined trajectories that I talked about, because those equations, they govern particles that are falling in toward the event horizon, but they're test particles. So these particles could also be black holes or objects.
Sure. Yeah. Right.
Yeah, but I didn't, directly have any input on that. Not directly, but indirectly. Yeah.
One last question, and then I'll let you go. But thank you so much for your time. It sounds kind of like Hawking radiation in some ways, where you get pair production, one of which gets to escape and the other one doesn't. How much comparison do you see there, or is that just incidental?
Well, the Hawking radiation is for like cosmological black holes. Okay, so it's a thermodynamic treatment. So it's more quantum, mechanical. Actually, I guess it's kind of, both of them. but you know, it uses like the virtual particles,
Right.
you know, to create the particles. And then the black holes that are radiating Hawking radiation, if I can recall, that they're like miniature black holes that are created in the early universe.
Oh, okay.
Right. And so I learned that like some time ago, but I noticed that people, they are talking about them as if they're like, you know, black holes, like stellar sized black holes or something like that. But the Hawking radiation is different because it involves the quantum mechanics.
Yeah, yeah. Okay. All right. Different kind of pair production, I guess,
Yeah.
using virtual particles instead of actual
Material particles
antiparticle. Yeah. Okay. Well, thank you so much. I appreciate your time, and it was very interesting. So, yeah.
Well, thank you, and thank you for having me, and I enjoyed it.
Yeah. All right. Thank you.
Okay. Bye-bye.
Bye-bye.